Okay, let's take a look at example program unit D1 page 4. Now this is actually a series of two example programs which is exactly the same program. We are going to solve the program using two different methods. So this is the first of the series of two programs which is essentially the same thing. So this is the bus stop. Okay, it's a very simple example. Bus stop can be simplified by rectangular, it's a cubic volume. The size is 1.5 feet deep, 5 feet by 2 feet. Okay, so water is filled up. Water is coming down and filling the bus stop. And then right now, at this moment, water depth is h. And then as time goes by, of course, you know this h gets bigger, bigger, and bigger, right? Okay? So at certain time later, this h becomes more than 1.5. It cannot be more than 1.5, so it's going to start overflow from the bus stop. So let's take a look at program statement. Okay? A bus stop is being filled with water from a faucet. The rate of flow from the faucet is steady at 9 gallons per minute. Let me just emphasize. The program says steady. Steady, this steady really means that this 9 gallons per minute flow rate does not change over time. Okay, so do not make a mistake that this is a steady state problem. This is actually unsteady problem. Just because the problem says some kind of steady, do not be fooled by it. This steady means this 9 gallons per minute doesn't change over time. So the flow rate Q incoming is a constant over time. Okay. The tap volume is approximated by a rectangular space. Okay. Let's estimate the time rate of change of the depth of water in the tub, which is dHdt in inches per minute. Alright, so let's move on to this side. So this is again the same picture, bus tub, cubic volume, which is copied from the program statement. Now first of all, you have to understand that this is non-steady program. What makes this program non-steady? Well, I'm going to try to solve this problem by defining control volume. Control volume is, let's say, bus stop itself is a control volume. So this is the cubic element bus stop, which I chose as a control volume. This is a fixed control volume. Okay, so I'm trying to solve this problem by choosing a fixed control volume, which is the bus stop itself, which is a reasonable choice. Then if I do that, obviously the water inside of the bus stop, which is control volume, keeps changing over time. I'm talking about mass of the water inside of the control volume keep increasing and increasing over time. So that actually makes this problem unsteady, totally unsteady problem. Okay? So the program says flow rate Q is steady. That means flow rate Q, this is B times A, is 9 gallons per minute, and it doesn't change over time. That's what it says, B times A. Okay? You can solve this program using either fixed control volume like this, or later you're going to find out. I'm going to show you how to solve the same problem using deforming control volume. Deforming control volume is, suppose if you define a control volume as water inside of the tub. It's not the tub, but the water inside of the tub. Obviously that is the control volume which is deforming. Okay? So we are going to take a look at that later, but first let's take a look at this problem by solved by fixed control volume. Okay. So first of all, this is the control volume. So you want to identify the control surface. Where is the control surface in this case? Control surface is the area that allows something to flow in or flow out. There's only flow in. There's no flow out. So take a look at this top surface. This top surface is going to cut through this incoming stream. So maybe around here. So this is where the top surface go across this incoming stream. This is your control surface. This is inflow. Okay. Area is given in the program. This is the area. Let's call this A sub j because that's what the program says. Cross-section area A sub j. This is a cross-section area of this incoming stream, which is virtually cut by this top surface. Okay. Then of course, this is a flow rate. Flow rate divided by cross-section area defines you the velocity. Velocity incoming. Let's call this B sub j. Velocity is vector. Okay. So this is the B sub j, velocity incoming. This is the cross-section area control surface in. Of course, you're going to define outward unit normal vector, let's say n sub j, outward unit normal vector, defined on this control surface in. Okay. Then now you are ready to apply continuity equation. So continuity equation is, of course, ddt over cv rho dv plus integral cs rho times v dot n dA is equal to 0. This is the continuity equation, the governing equation. Okay, so this is obviously not the steady state problem. You cannot drop this term. Too bad. You have to carry this term throughout your analysis because it's not a steady problem. This is how much mass of the water inside of the control volume change over time. It is not 0. It is some kind of positive value. This one is a mass flow rate across the control surface. Of course, you have one incoming mass flow of water. Okay. So now one thing, since I defined fixed control volume as a bathtub itself, so the reality is, as the water gets in, start taking over the volume within the control volume, the air is actually moving out of the control volume also. So you can develop two equations, continuity for water and continuity for air, and which is vice versa, or flip-flop to each other. As the water takes place, air needs to get out. Okay, one is increasing, one is decreasing. So in this analysis, I'm going to completely ignore about the air escaping from the control surface. Okay, so let's just consider water in the control volume. And water mass flow rate. Across control surface. So let's be careful. I'm purposely ignoring the air escaping as the water gets in. Okay? So let's consider, let's think about this meaning. So this is time rate of change ddt. This is an integral of density over volume. Density is constant. That's one nice feature here. This is the water, so density of water doesn't change. So this is, well, let's just put the bracket density of water. Keep in mind this is constant. Constant, and you deep, this is 1.94 slugs per cubic foot. It doesn't change. Water is liquid, liquid is incompressible. This is the integral over volume. So what is the volume of water inside of the control volume? Well, of course, this is the water. The water volume is 5 times 2 times h. Yeah, sure. So 5 feet times 2 feet times h. Wait a second, is that really a water volume? No. This portion of the incoming stream is also water, and then inside of the control volume also. So you're talking about water volume this much. So this much volume. So you have to obviously add volume of water of this much. Okay? So that is essentially 1.5 feet minus h multiplied by cross-section area A sub j. Okay? So keep that in mind. This is a volume of water within the fixed control volume we defined. So integral over the control volume dV gets you the volume of water inside of the control volume. That's this. Multiplied by density of water and taking the time rate of change of it is going to be this term. Okay? Good. How about that? This one only has control surface n. So if you take a dot product b dot n, it's going to be a negative b, right? So this one is, of course, density of water. This one, and then taking a dot product gets you negative of b a. B times, well, sorry, negative of b. Sorry about that. Negative of b. If you take a dot product, negative of bj. Integrated over the area. The area you're talking about aj. So that is mass flow rate in across this control surface in, right? If you add those things together, you got 0. Interesting. So we can proceed from here. So let's move on a little bit more. So left hand side is ddt. Oh, before doing that, this is the density of water constant. This is also density of water constant. So if this is constant, this goes here, actually outside of ddt. This is a constant. Good news is you can cancel out densities. Let's divide both sides by density of water. Get rid of density. Boom. Oh, that's nice. It's such a nice thing being constant density. Okay. So if you do that, left hand side becomes ddt. This is a 10 feet square h. 10 feet square times h plus, okay, within the bracket, 10 feet square times h plus 1.5 feet times aj, 1.5 feet times aj minus h times aj. this one, move it to the right hand side. So this is equal to B, J, A, J. By the way, velocity Bj multiplied by cross-section area Aj, this actually gets you flow rate Q, which we know 9 gallons per minute. Okay. So let's just do a little bit more. This is going to be ddt of 10 feet square h. This is ddt of 1.5 feet times aj minus ddt of h times aj is equal to q, right? So first of all, this middle term, A sub j, this is cross-section area, which is constant. It's just a constant value. 1.5 feet, this is also constant value. So this is essentially just a constant. It does not depend on time. So if you take a time rate of change of constant value, it's going to be 0. So this term is going to be gone. This one will become 10 feet square times dH dt, right? This one is Aj times dH dt, right hand side is Q. So this is dH dt 10 feet square minus Aj is equal to Q. So the question is, what is the dH dt rate of change of the water depth change? So as the water gets in, this H becomes deeper and deeper and deeper, actually higher, higher, higher height. So water gets filled. This H is going to increase. So that's dH dt. Okay? So dH dt, come to think about, this is actually the velocity on this water surface is moving upward direction. Okay? So this is the velocity of this water surface moving upwards. So this is the velocity, which is equal to whatever the flow rate, this is 9 gallons per minute, divided by 10 feet square minus Aj. Okay? So this is a rate, okay, so this is a rate of time rate of change of the depths of water. If you plug in the value, you're going to get inch per minute. So how many inches of the water depth increase you can observe per every minute? This is essentially the velocity of the water surface, or time rate of change of H, time rate of change of H, water depths. Okay? So we're going to stop here for a moment, and then we're going to revisit this same problem. Okay? We are trying to solve the same exact problem using deforming control volume, and then we are going to discover if we get the same exact answer or not. Okay? So let's stop for now.